Something is deeply, catastrophically wrong with the universe, and scientists are only now realizing it. James Webb stared at the oldest light in existence and found galaxies that should not be there, fully formed, massive, at just 280 million years after the Big Bang. Then it found oxygen, impossible at that age. Then black holes so enormous at 400 million years, they defy every known law of physics. And then, the most terrifying discovery of all. The universe is expanding, but nobody agrees how fast. 2 telescopes, 2 answers, 0 explanation, and the deeper James Webb looks, the worse it gets. The true scale of this universe is terrifying, not because of how large it is, but because the more precisely we look, the less we recognize it. And tonight, you are going to see exactly how deep that rabbit hole goes. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. On Christmas morning, 2021, while most of the world was opening gifts and sitting around warm tables, humanity quietly did something it had never done before. We launched the most complex machine ever sent to space. Not the most powerful, not the largest. The most complex, by a significant margin. A machine so intricate, so demanding in its engineering, that scientists and engineers spent decades just rehearsing all the ways it could fail. And what they found was terrifying. The James Webb Space Telescope had 344 single points of failure. 344 individual moments where, if one component behaved incorrectly, just once, just slightly, the entire mission would be lost. No second chances, no repair crew, no going back. And we sent it anyway. To understand why this matters, you need to understand what Webb actually is, because most people have the wrong picture. The common assumption is that Webb is simply a better Hubble, a newer model, an upgrade. But that comparison misses something fundamental. Hubble sees light that human eyes can see, the same visible spectrum you use to read these words, to recognize faces, to watch a sunset. Webb sees something entirely different. Webb sees infrared light, heat radiation essentially, wavelengths of light that are completely invisible to human eyes and to Hubble's instruments. This is not a minor technical distinction. Infrared light behaves differently than visible light in one critical way. It can travel through clouds of cosmic dust that block visible light entirely. And dust, it turns out, is everywhere in the early universe. Everywhere that the most interesting things are happening. Think of it this way. Imagine trying to study a forest fire through a thick wall of smoke. Hubble could only see the smoke. Webb sees through it, directly to the fire. Webb's primary mirror stretches 6.5 meters across, roughly 21 feet. To give that some personal scale, if you laid that mirror flat in a room, it would cover the floor of a modest apartment from wall to wall. And unlike Hubble, which launched in one rigid piece, Webb's mirror had to fold up like origami to fit inside the rocket. Then, once in space, it had to unfold itself, perfectly, autonomously, one mechanism at a time, at a distance of 1 million miles from Earth. That is roughly 4 times the distance between Earth and the Moon. Too far for any repair mission, too far to reach, too far to fix. Every single step had to work, and every single step did. In July 2022, NASA released Webb's first deep field image, and if you have seen it, you already know it does something to you. What fills the frame is not empty space. What fills the frame is galaxies, thousands of them, smeared and stretched and clustered into every corner of the image, each one a system containing hundreds of billions of stars, some of them distorted into arcs by the gravitational pull of other galaxies bending their light. Every single smear of color in that photograph is a galaxy, not a star, a galaxy. And the patch of sky this image covers? Hold a grain of sand at arm's length. The sky behind that grain of sand, that is what you are looking at. Now, here is what scientists expected to find inside that image. For 40 years, cosmologists had operated under a model called lambda cold dark matter, or simply the standard model of cosmology. It was not a guess. It was the product of decades of observation, mathematical modeling, and rigorous testing. And one of its core predictions was this: the early universe was simple, smooth, and slow. In the first few 100 million years after the Big Bang, matter was spread relatively evenly. Structure, galaxies, clusters, the vast architecture of the cosmos formed gradually, hierarchically, over billions of years. Small clumps of gas came together first. Then those clumps merged into larger ones, then larger still, like dust gathering into piles, slowly, patiently, across cosmic time. The universe was expected to look young when Webb looked back to it. Sparse, immature, full of the raw, unformed material of a cosmos, still learning how to build things. That is what 40 years of careful science predicted. That is not what Webb found. In January 2023, a team led by Emma Curtis Lake confirmed something that stopped cosmologists mid-sentence. Webb had detected 4 galaxies at what astronomers call redshifts between 10.3 and 13.2. Redshift is the way we measure cosmic distance and age. The further away an object is, the more the expansion of the universe has stretched its light toward the red end of the spectrum, like pulling taffy until its color changes. A redshift of 10.3 places a galaxy, approximately 340 million years after the Big Bang. A redshift of 13.2 places one, just 320 million years after it. For context, the universe is 13.8 billion years old. These galaxies existed when the universe was less than 3% of its current age. To put that in human terms, if the universe's entire history were compressed into one average human lifetime of 78 years, these galaxies were already formed and burning bright during the first few weeks of that life. These were the most distant galaxies ever spectroscopically confirmed, meaning scientists did not just photograph them and guess their distance, they measured it precisely, splitting their light into its component wavelengths, the way a prism splits sunlight, and reading the chemical signatures directly. But their distance was not the problem, their size was. 1 month later, in February 2023, Ivo Labbé and his team at Swinburne University announced something that deepened the crisis considerably. They had found 6 galaxies, all of them within 500 to 700 million years of the Big Bang, each one containing between 10 billion and 100 billion times the mass of our Sun. The lower end of that range, 10 billion solar masses, is already staggering. Our entire Milky Way galaxy contains roughly 50 to 60 billion solar masses of stars. So these objects, at the very dawn of cosmic time, already held stellar mass comparable to a full-grown modern galaxy. Scientists looked at those numbers and ran the calculation. To build that much mass that fast, starting from the smooth, diffuse hydrogen and helium that the Big Bang actually produced, the universe would need to convert nearly 100% of available gas directly into stars. 100%. Normal star formation, across the entire history of the universe, averaged over billions of years, operates at between 5 and 10% efficiency. Think of it like burning wood. In a normal fire, you lose enormous energy to heat, to smoke, to incomplete combustion. Only a fraction of the fuel becomes useful flame. Star formation works the same way. Gas clouds collapse under gravity, but turbulence, radiation pressure, and magnetic fields disrupt the process constantly. Most of the raw material never becomes a star at all. 5 to 10% is the observed, measured, well-understood ceiling. 100% is not a ceiling. 100% is physically unprecedented. It means every single atom of available gas converted directly and immediately into stellar mass, with nothing lost, nothing wasted, no disruption, no delay. That is not how gas behaves. That is not how gravity behaves. That is not how anything in known physics behaves. And it gets worse. When Labbé's team calculated how many such galaxies Webb should be finding, based on the Standard Model's predictions, they expected these objects to be extraordinarily rare, cosmic outliers, statistical oddities at the very edge of what was possible. Instead, luminous early galaxies were appearing approximately 10 times more often than the Standard Model predicted. Not slightly more, not twice as often, 10 times. Let that settle for a moment. The model that governed cosmology for 4 decades, the model built from the most precise measurements humanity had ever made of the cosmic microwave background, the echo of the Big Bang itself, predicted a universe that Webb simply did not find. Webb looked at the early universe and found something more crowded, more massive, more fully formed than anyone's equations allowed for. Cosmologists had a phrase for results that contradicted predictions by this margin. They called it attention. This was not attention. This was a fracture. Now, before we go further, it is worth being precise about something, because science demands it, and because the honest answer is more interesting than the dramatic one. The current leading explanation is not that the Big Bang model is simply wrong. The equations that describe the Big Bang itself remain among the most precisely tested in all of physics. What Webb appears to be challenging is the part of the model that comes after, the part that predicts how structure grows, how galaxies assemble, how matter organizes itself across cosmic time. That part of the Standard Model may require significant revision. Some researchers have proposed that early galaxies were simply more efficient at forming stars than modern ones, that something about the conditions of the early universe, perhaps fewer disruptive forces, perhaps different gas dynamics, produced a brief window of extraordinary productivity. Others suggest that the early universe contained structures seeded by physics we have not yet discovered, physics beyond the Standard Model of particle physics itself. What is clear, what the data shows without ambiguity, is that the universe in its infancy was doing something our models did not anticipate, something faster, something denser, something more capable than 40 years of careful theorizing predicted. And Webb had been operational for less than a year when it found this. That image, the one that fits behind a grain of sand held at arm's length, contained thousands of galaxies, and somewhere inside those thousands of galaxies, distributed across billions of years of cosmic history, were signatures that the Standard Model had never prepared us for. But the galaxy formation crisis was, in a sense, the most forgivable surprise. Galaxies are vast, complex systems. Maybe the models simply underestimated how efficiently they could build themselves in the right conditions. Maybe there is a physical explanation that fits cleanly into known physics once someone finds the right equation. What came next was harder to forgive, because what came next was not about how fast a galaxy could form. It was about what was already inside one, at a moment in cosmic history when, according to everything we understood, that thing could not yet exist. In a galaxy burning at the edge of observable time, Webb detected oxygen. And oxygen, by every law of physics we know, should not have been there yet. To understand why oxygen should not have been there, you need to understand something that most people have never been told about the air they are breathing right now. Every single oxygen atom in your lungs, in your blood, in your bones, in every molecule of water that has ever passed your lips, was forged inside a star that lived and died before our sun was born. Oxygen is not a natural product of the universe. The universe, left to its own earliest devices, does not make oxygen. And the fact that Webb found it glowing inside a galaxy at the very edge of observable time is not just surprising. It suggests the early universe was doing something that our entire timeline of cosmic history says was impossible. Let's be precise about what the Big Bang actually produced. When the universe was born, in its first few minutes of existence, the temperatures were so extreme that only the simplest atomic nuclei could form. The Big Bang produced hydrogen, the lightest element, a single proton orbited by a single electron, the most basic building block in nature. It produced helium, and it produced trace amounts of lithium, the third element on the periodic table. That was it. 3 elements. The entire cosmos in its infancy was made of almost nothing but hydrogen and helium, a vast, hot, featureless fog drifting outward in all directions. Oxygen, the 8th element, far more complex, requires a completely different process, a process that cannot happen in the open universe, a process that can only happen inside a star. Deep inside a massive star, gravity compresses hydrogen with such force that it fuses into heavier and heavier elements, climbing the periodic table step by step. Helium, then carbon, then nitrogen, then oxygen. This process is called stellar nucleosynthesis, meaning stars are the universe's factories for building complex chemistry. But those factories are not permanent. A massive star, one large enough to produce significant oxygen, burns through its fuel at a ferocious rate. And when it exhausts that fuel, it collapses catastrophically and explodes. The explosion is called a supernova, and it scatters everything the star spent its life building. All that oxygen, all that carbon, all those heavier elements, outward into the surrounding gas clouds. Only then, after that explosion, can the oxygen mix into new clouds of gas. Only then can new stars form from that enriched material. Only then can a second generation of stars carry oxygen in their bodies and in the planets that form around them. This is the chain. First stars ignite, they live, they die violently, they seed the gas around them with the elements they built. Then new stars form from that seeded gas. This is the only known path from a hydrogen universe to an oxygen universe, and every step in that chain takes time. In May 2024, a team using Webb confirmed the most distant galaxy ever spectroscopically verified at that point in scientific history. Its name is JWST 14-0, and it existed at a redshift of 14.32, meaning we are seeing it as it was just 290 million years after the Big Bang. 290 million years sounds like a long time, but set it against the universe's current age of 13.8 billion years, and it represents roughly 2% of all of cosmic history. If you compress the universe's entire timeline into a single calendar year, 290 million years would place us in the first week of January. Not even the second week, the first. And inside this galaxy, Webb detected oxygen. Let's think carefully about what that requires. Massive stars, the kind capable of forging and distributing significant oxygen, live between approximately 3 million and 10 million years before they explode. 3 to 10 million years. That sounds like a long time in human terms. In geological terms, 3 million years ago, our earliest ancestors were just beginning to walk upright across the African savanna. But against the 290 million years available in the early universe, 3 to 10 million years per stellar generation is actually encouragingly fast. The problem is not any single step. The problem is the sequence. Picture it this way. Imagine you are trying to build a house, but before you can lay a single brick, an entire forest must grow from bare soil, be harvested for timber, milled into planks, dried, transported, and cut to size. Every step depends on every previous one. None can be skipped. None can happen simultaneously, and you have been given a deadline. The universe, in those first 290 million years, had to complete every stage of that sequence, from the very first stars igniting out of primordial hydrogen, to those stars living their full lives, to their supernova explosions enriching the surrounding gas, to that enriched gas collapsing into new stellar generations, before a single atom of oxygen could appear in the way Webb measured it. Before Webb, cosmologists had estimated that 290 million years after the Big Bang was barely past the moment when the very first stars would have begun to switch on at all. The standard timeline placed the ignition of the first stellar generation somewhere between 100 and 250 million years after the Big Bang, meaning that when JD's JWST 14-0 was burning with oxygen, the universe may have only just finished lighting its first stars a few tens of millions of years earlier. That does not leave room for multiple stellar generations to live and die, not even close. And then, in January 2026, the record broke. A new galaxy, designated MOMZ 14, was confirmed at a redshift of 14.44, just 280 million years after the Big Bang. 10 million years earlier than JD's JWST 14-0. 10 million years is a meaningful gap at this stage of the universe. That is roughly the full lifespan of one generation of massive stars. NASA's own statement about MOMZ 14 was unusually direct. They said it looks nothing like what we predicted, not different from expectations, not slightly anomalous. Nothing like what we predicted. When space agencies use language like that in official communications, it signals something significant. MOMZ 14 was described as brighter than expected, more compact than expected, and more chemically enriched than anyone had anticipated finding at that distance in time. And like JD's JWST 14-0, it showed the chemical signatures of a universe that had already been through multiple cycles of stellar birth and death. But MOMZ 14 added something else: elevated nitrogen levels. Nitrogen, like oxygen, is not primordial. Nitrogen is also forged in stars and scattered in supernovae. Its presence, alongside oxygen, at 280 million years, compounds the timeline problem rather than softening it. This is not one anomalous element. This is a galaxy that, by its own chemical fingerprint, has already lived through what appears to be generations of stellar cycling at a moment in cosmic history when the first generation of stars had barely had time to light up. The early universe was not slow, sparse, and elementary. Something had been building there far earlier and far faster than any model anticipated. Here is the impossibility stated plainly. From the Big Bang to the moment Webb photographed JD's JWST 14-0, 290 million years passed. During that window, the following had to occur in sequence without overlap, without shortcuts. The universe had to cool enough for hydrogen to clump under gravity. Those clumps had to collapse into the first stars. Those first stars had to ignite. They had to burn through their hydrogen fuel, which, for the most massive stars, takes a minimum of roughly 3 million years. They had to exhaust that fuel and explode as supernovae. The explosion debris had to expand into the surrounding gas, cool and mix. That enriched gas had to collapse again under gravity. New stars, a second generation, had to form from it, and that second generation had to have already been burning long enough to produce a galaxy bright and massive enough for Webb to detect. All of that in 290 million years. Brant Robertson of the University of California at Santa Cruz, one of the lead researchers on this finding, described the oxygen detection as completely unanticipated. That is a careful, measured phrase from a careful, measured scientist. What it means, in practical terms, is that no version of the standard model, run at any setting, produces this result. The finding did not sit at the edges of the model's predictions. It sat outside them entirely. And here is the detail that makes this more than a calibration problem. Webb's measurement of oxygen in JD's JWST 14-0 did not come from Webb alone. In March 2025, astronomers combined Webb's infrared data with observations from ALMA, the Atacama Large Millimeter Array in Chile, an entirely separate telescope system, operating on entirely different physical principles, measuring different wavelengths of light across a distance of 7,500 miles, or 12,000 kilometers. Two independent instruments, two independent methods, one confirmed result. This is not a telescope artifact. This is not a calibration error. This is not noise in the data. The oxygen is real, the timeline is real, and the two are incompatible with our current understanding of how the early universe assembled itself. So, What does this require? The most conservative interpretation among researchers, and even this is significant, is that our models of early star formation need fundamental revision. Specifically, it suggests that the very first generation of stars, sometimes called population 3 stars, may have been far more massive and far shorter lived than current models assume. A more massive first star burns hotter, processes more material, and dies faster. If the first stellar generation was systematically more extreme than we calculated, the chemical enrichment cycle could have been compressed, not eliminated, but accelerated to a degree that makes the timeline less impossible. But here is what is important to understand about that explanation. It is a hypothesis, a reasonable one, grounded in known stellar physics, but as of early 2026, it has not been confirmed. And even if it holds, it raises its own questions, because producing stars of that extreme mass requires conditions in the early universe that the standard model also does not fully predict. What the oxygen discovery demands at minimum is a fundamental restructuring of the universe's early chemical timeline. Not a tweak, not a parameter adjustment, a restructuring. The universe, in its very first moments of coherent structure, was chemically evolving at a pace that our 40 years of carefully constructed models simply did not foresee. The first galaxies were not infants stumbling into existence. They arrived already carrying the scars of multiple stellar lifetimes, already seeded with elements that took generations to build, already, in some deep structural sense, older than the universe had time to make them. The oxygen finding reframes everything we thought we knew about the early universe's pace. The first few 100 million years were not a slow dawn, not a gentle ignition. Something was happening there, fast, violent, chemically complex, at a rate the models cannot yet explain. But oxygen, as disturbing as it is, at least involves a process we understand. Stars form, burn, explode, enrich. The timeline is wrong, but the mechanism, the basic chain of cause and effect, is familiar. We know stars. We know supernovae. We know how elements are made. The numbers do not fit, but the story, at least, involves things we recognize. What Webb found next did not involve a familiar story. What Webb found next involved objects that, under known physics, cannot exist at all. Not objects that form too fast, not objects that arrive too early, objects that, given the maximum theoretical rate at which they can grow, simply should not be there, not in any version of any timeline, fast or slow. Black holes, fully formed, catastrophically massive, sitting in galaxies that were barely old enough to contain a single stellar generation, let alone the hundreds of millions of years of sequential growth that black hole physics demands. The oxygen crisis told us the early universe was older than its age. The black hole crisis is about to tell us something far harder to absorb. The oxygen crisis had a logic to it, even in its impossibility. Stars form, they burn, they explode, they seed the gas around them. It happened too fast, staggeringly, inexplicably fast, but the mechanism itself was familiar. We understood every step in the chain. We just could not explain why the chain completed so quickly. What Webb found next had no familiar chain, no sequence of known steps that, however accelerated, could arrive at the answer. What Webb found next were objects that physics says cannot exist at the moment they were found, not objects that form too efficiently, not objects that beat an expected deadline by a narrow margin, objects that should not be there at all. To understand the crisis, you need to understand how a supermassive black hole is supposed to form. Every large galaxy in the universe, including our own Milky Way, has a supermassive black hole sitting at its center. Ours is called Sagittarius A star, and it contains about 4 million times the mass of our Sun. 4 million solar masses, compressed into a region smaller than our entire solar system. The Sun, for reference, is so large that roughly 1 million Earths could fit inside it. Sagittarius A star has consumed 4 million of those, and then compressed all of it beyond any size we can directly observe. But Sagittarius A star is considered modest by cosmic standards. Some supermassive black holes contain billions of solar masses, and the question cosmologists have long wrestled with is a simple one. How do they get that big? The process is called accretion. A black hole grows by pulling in surrounding gas, dust, and stellar material, swallowing it, adding its mass to its own. Think of it like a drain in a bathtub, steadily pulling water inward. The more it consumes, the more its gravity pulls in additional material. Over long stretches of time it grows. But here is the critical constraint. There is a hard physical ceiling on how fast a black hole can feed itself, and it has a name, the Eddington limit. Named after the British astrophysicist Arthur Eddington, it describes the point at which a black hole's own feeding process becomes self-defeating. As a black hole swallows material, that material heats to extreme temperatures and radiates outward with enormous energy. At the Eddington limit, the outward pressure of that radiation becomes strong enough to push the incoming gas away, essentially blowing the black hole's own food supply off the table before it can be consumed. Picture a fire that generates so much heat that it evaporates its own fuel before the fuel can burn. The fire cannot grow beyond a certain size, no matter how much combustible material surrounds it, because its own intensity prevents consumption. A black hole at the Eddington limit faces exactly the same problem. It is feeding as fast as physics allows, and it cannot go faster. Under the Eddington limit, growing a black hole from the mass of a single collapsed star, roughly 10 to 100 times the mass of our Sun, into something containing millions or billions of solar masses takes hundreds of millions of years at minimum, likely longer. The math is straightforward and well tested. Cosmologists had used it confidently for decades. They were wrong. In 2024, Roberto Maiolino and his team at the University of Cambridge published findings that forced a confrontation with that math. Using Webb, they confirmed a supermassive black hole inside a galaxy called GNZ11. This galaxy existed just 400 million years after the Big Bang. 400 million years, which, against the universe's 13.8 billion year lifespan, represents less than 3% of all of cosmic time. If you compress the universe's entire history into a single day of 24 hours, 400 million years would place us at roughly 41 minutes past midnight. The rest of the day, more than 23 hours of it, had not yet happened. And inside GNZ11, at 41 minutes past cosmic midnight, sat a black hole containing 1.6 million times the mass of our Sun. 1.6 million solar masses at 400 million years of age. Run the Eddington limit growth equations backward from that mass, and you encounter the problem immediately. For a black hole to reach 1.6 million solar masses by 400 million years after the Big Bang, even feeding at the absolute maximum rate physics, allows, without pause, without interruption, from the very first moment the first stars could have produced the seed black holes needed to start the process. The math does not close. The timeline is too short. The available time is not enough. But that was not the only case. Separately, a combined detection using both Webb and the Chandra X-ray Observatory, two entirely different telescopes measuring entirely different forms of radiation, found a black hole estimated at somewhere between 10 million and 100 million solar masses, at just 450 million years after the Big Bang. Two independent instruments, two independent detections, two black holes whose existence under known physics cannot be explained by any accepted mechanism. Both exist far earlier than maximum theoretical growth rates can produce. And then, in March 2024, Webb revealed something stranger still. Researchers analysing Webb's deep field data catalogued a new class of object they had never seen before. Compact, intensely red, appearing throughout the early universe between roughly 600 million and 1.6 billion years after the Big Bang. Scientists called them, with unusual informality for a technical discovery, little red dots. By 2025, 341 of them had been catalogued. Not one or two, not a handful of anomalies at the edge of detection. 341 distinct objects, spread across Webb's observations, each one posing the same set of unanswerable questions. Each little red dot is extraordinarily compact. Their radii measure under roughly 500 light-years across. To put that in perspective, our Milky Way galaxy stretches approximately 100,000 light-years from edge to edge. 500 light-years is 1/200th of that. Imagine compressing the entire Milky Way, every star, every nebula, every cloud of interstellar gas, into a sphere the size of a small town compared to the continent it currently occupies. That is the spatial scale of a little red dot. And yet, inside that extraordinarily compressed volume, something is generating light at a rate that defies easy explanation. But the truly disturbing finding was not their size, and it was not their brightness. It was the ratio. In the present-day universe, supermassive black holes are large, but they are modest compared to their host galaxies. Across the modern cosmos, a galaxy's central black hole typically contains approximately 1/10% of that galaxy's total stellar mass, meaning the black hole accounts for roughly 1 part in 1,000 of everything the galaxy has built in stars. Sagittarius A star, at 4 million solar masses, sits inside a Milky Way containing somewhere between 50 and 60 billion solar masses of stars. The ratio holds. 1 black hole, 1 galaxy, an enormous gap between them. That ratio is not an accident. It reflects the physics of how galaxies and black holes grow together over billions of years, a kind of gravitational coevolution, each regulating the other across cosmic time. In the little red dots, that ratio is obliterated. The central black holes in little red dots weigh up to 40% of their host galaxy's entire stellar mass. Not 1/10 of 1%. 40%. That is a difference of 400 times. In a little red dot, the black hole does not sit quietly at the center of a vast galaxy. The black hole and the galaxy are nearly the same size. The black hole representing nearly half of all the mass in stars the galaxy has managed to produce. Think about what that means structurally. Imagine a city where the city hall, just the one building at the center, weighs nearly as much as every house, every apartment block, every skyscraper, every bridge and every road in the entire city combined. That is the mass relationship between a little red dot's black hole and its host galaxy. The relationship makes no sense under any model of how galaxies and black holes grow together. And as of early 2026, researchers are openly stating that the little red dots represent a class of object they cannot yet identify or explain. Not objects they are still studying, objects they cannot yet explain. Let's be careful here, because careful is what the science demands. Some researchers have proposed that the little red dots might not be entirely what they appear. The extreme redness of these objects could, in principle, result from large amounts of dust inside or around them, absorbing bluer light and re-radiating it as infrared, making them appear more compact and more luminous in certain wavelengths than they actually are. Webb, by its nature, is an infrared telescope, and infrared observations, while extraordinarily powerful, come with their own interpretive complexity when dust is involved. This is a real debate among researchers, not a fringe objection, a genuine scientific disagreement between teams with access to the same data. But here is what the debate does not resolve. Even if some of the apparent luminosity or compactness of the little red dots is modified by dust effects, the black hole mass estimates in the confirmed cases, including the ones from GNZ11 and the Chandra combined detection, come from independent measurements of how fast gas is orbiting the black hole. Gas that orbits faster requires more gravity to hold it in orbit. More gravity requires more mass. That measurement does not depend on dust or brightness or infrared interpretation. It depends on velocity. And velocity is something both Webb and Chandra can measure with high confidence. The mass is real. The early timestamp is real. The ratio problem is real. What remains genuinely unresolved is the mechanism, the explanation for how any known process could have produced these objects this early, at this mass, in the time available. Several theoretical proposals exist. Some researchers suggest that the very first black holes in the universe were not formed from stellar collapse at all, but rather from the direct collapse of enormous primordial gas clouds, bypassing the stellar phase entirely and creating what are sometimes called direct collapse black holes. This would provide a much more massive starting point from which Eddington limited growth could proceed. Others suggest that the Eddington limit itself may be violated in the extreme conditions of the early universe, that brief chaotic bursts of super Eddington feeding could dramatically accelerate growth in ways that modern, calmer cosmic environments simply do not permit. Both remain hypotheses, neither has been confirmed, and neither fully accounts for every object Webb has found. The universe built black holes first, massive, dominant, disproportionate, and then apparently the galaxies around them slowly caught up. That sequence is the reverse of what the standard model predicted, not a minor reversal, a fundamental one. Everything Webb has found in its first few years of operation follows a pattern. The early universe was not simple, not sparse, not slow, not the quiet, gradual, orderly place our models predicted. Galaxies too massive, chemistry too advanced, black holes too enormous, and all of it arrived too soon, as if the universe had secretly been running the show for longer than the Big Bang itself allows. But here is what we have not yet done. We have spent this time looking inward, toward the earliest galaxies, the most distant objects, the smallest and most ancient structures. We have been, in a sense, examining the universe through a microscope trained on its infancy. We have not yet stepped back. We have not yet asked what the universe looks like at full scale. Not the scale of galaxies, not the scale of clusters, the full, uncompressed, actual scale of everything, from one end of the observable cosmos to the other. And when you do step back that far, when you let the numbers speak at their true, unfiltered magnitude, the universe does not become more familiar. The structures Webb found in the early cosmos are not isolated anomalies. They are clues to a larger architecture, an architecture so vast, so structured, so far beyond what the standard model predicts, that the anomalies of the early universe begin to feel like symptoms of something much deeper. The universe is not just bigger than we imagined. What we can actually see is only a fraction of what surrounds us, and the fraction we cannot see may be infinite. We have spent considerable time looking at the universe up close, peering into its infancy, counting its impossible galaxies, measuring its inexplicable black holes, and through all of it, there has been an implicit assumption that we have at least been looking at the universe, the whole thing, or close enough to it. That assumption is wrong. What we call the observable universe is not the universe, not even close. The observable universe is simply the portion of reality from which light has had enough time since the Big Bang to reach us. A bubble, a window, a single cross-section of something that extends, in all likelihood, vastly, almost inconceivably, beyond everything Webb has ever photographed or will ever photograph. And when you begin to truly absorb what lies inside, even just the portion we can see, you understand why scale itself becomes the story. Before we go further, there is a number that needs explaining, because it surprises almost everyone the first time they encounter it. The observable universe stretches approximately 93 billion light-years across. A light-year is the distance light travels in 1 year, moving at roughly 300,000 kilometers, or about 186,000 miles, every single second. In 1 year, light covers approximately 9.5 trillion kilometers, or about 5.9 trillion miles. That is 1 light year. Now multiply that by 93 billion. But here is what stops people. The universe is 13.8 billion years old. How can the observable universe be 93 billion light years across if nothing travels faster than light, and the universe has only existed for 13.8 billion years? Shouldn't the edge be only 13.8 billion light years away? The answer reveals something profound about the nature of space itself. Space is not a fixed container. Space expands. The galaxies at the edge of our observable universe were not always that far away. They were much closer when their light began its journey toward us. But while that light travelled across billions of years, the space it was crossing continued to stretch outward in all directions. So by the time that ancient light arrived at our telescopes, the galaxy that emitted it had been carried by the expansion of space to a position now roughly 46 billion light years away from us, on each side. The universe did not break the speed of light. Space itself, carrying galaxies along with it like raisins in rising bread dough, expanded faster than light can cross it. The observable universe is 93 billion light years across, not because anything moved that fast, because space itself grew. Inside that 93 billion light-year bubble, astronomers estimate there are more than 2 trillion galaxies. 2 trillion. That number needs a moment. A trillion is a million millions. 2 trillion is 2 million millions. If you tried to count to 2 trillion at the rate of 1 number per second, without sleeping, without stopping, it would take you roughly 63,000 years. The last time humans were counting at all, making marks on bones and cave walls, was roughly 50,000 years ago. 2 trillion seconds would carry you further back in time than the earliest known evidence of human symbolic thought. And each of those 2 trillion galaxies is itself a system. Each contains hundreds of millions to hundreds of billions of individual stars, each star potentially surrounded by planets. The scale compounds so rapidly, so relentlessly, that the mind offers resistance, not from confusion, but from a kind of protective numbness. The human brain was built for savannas and social groups, not for this. But here is what makes it stranger still. Those 2 trillion galaxies are not scattered randomly. They are organized. The universe, at the largest scales, forms what astronomers call the cosmic web, a vast, 3-dimensional network of structure, dark matter filaments stretching across hundreds of millions of light years, with galaxy clusters and superclusters concentrated at their intersections, galaxy sheets spanning enormous distances, and between all of it, vast, empty regions called voids. The cosmic web looks, in visualizations, remarkably like the neural network of a human brain. Clusters at the nodes, filaments connecting them, and vast empty spaces between. That resemblance is structural, not coincidental. Both systems are shaped by the same underlying mathematics. Networks of nodes connected by threads, with most of the volume being empty space. But the voids are where the true scale of this architecture becomes disturbing. In 1981, astronomer Robert Kirshner and his colleagues were surveying a region of the sky in the constellation Boötes. They expected to find what surveys usually found, a relatively uniform distribution of galaxies, with the usual clustering and some empty patches between clusters. What they found was a sphere of near total emptiness, roughly 330 million light-years across. 330 million light-years. To put that distance in perspective, if you shrank our entire Milky Way galaxy down to the size of a single grain of sand, and then laid 330 million such grains of sand end to end, you would just barely cross the Boötes void. The void is so enormous that it spans roughly 3% of the entire diameter of the observable universe. The standard model predicted that a void of this size would still contain thousands of galaxies, thinly spread, sparsely distributed, but present. Gravity, operating across billions of years, was not expected to completely evacuate a region this large. The Boötes void contained roughly 60 galaxies, not thousands, 60. In a sphere 330 million light-years wide, where physics predicted thousands of galaxies should exist, astronomers found 60. The void is not empty in the way a clean room is empty. It is empty the way the space between solar systems is empty, a vacancy so profound that even the most sensitive instruments of 1981 struggled to find anything inside it at all. Scientists have proposed various explanations. Some suggest the Boötes void formed from the merger of several smaller voids over cosmic time. Others point to the way galaxy formation itself redistributes matter, pulling it toward filaments and leaving behind the regions that seed into voids. No single explanation has been fully confirmed. The Boötes void remains one of the largest and emptiest confirmed structures in the observable universe, but it is not the largest void we know of. Not even close. The Milky Way sits inside a void, not a small one, not a modest underdensity in the cosmic distribution of matter. The KBC void, named for the astronomers Keenan, Barger and Cowie, who mapped it in 2013, stretches approximately 2 billion light-years across. That is roughly 6 times larger than the Boötes void. 6 times. A sphere of relative cosmic emptiness, 2 billion light-years in diameter, and our galaxy sits somewhere near its center. 2 billion light-years of relative emptiness in every direction. Our nearest large galactic neighbor, the Andromeda Galaxy, is about 2.5 million light-years away. The KBC void extends roughly 1 billion light-years in every direction from us. Andromeda sits comfortably inside it, as does everything in our local neighborhood of the cosmos, as does the local group of galaxies, and the Virgo cluster beyond it. All of it, the entire region we can call our cosmic neighborhood, sits within this vast underdensity, surrounded by denser walls of galaxies at the void's edges, like the inner surface of an enormous bubble. This matters for reasons beyond pure scale. The KBC void may actually be contributing to one of the most significant unresolved tensions in modern cosmology, the disagreement between different measurements of the universe's expansion rate. If we live inside a void, the local expansion rate around us may differ slightly from the global average, which would show up precisely as the kind of discrepancy that physicists have been struggling to explain. Living inside a void is not a neutral fact. It is a fact with potential consequences for our most fundamental measurements of the cosmos. In 2014, a team led by Brent Tully at the University of Hawaii published a landmark study in the journal Nature. Using precise measurements of how galaxies move, not just their positions, but the gravitational flows pulling them toward concentrated mass, they mapped our cosmic address with unprecedented clarity. Our galaxy belongs to a supercluster, a vast gravitationally bound region of hundreds of thousands of galaxies, named Laniakea. The word is Hawaiian, meaning immeasurable heaven. Laniakea stretches approximately 500 million light-years across in its widest extent. It contains more than 100,000 individual galaxies. Our Milky Way sits near the edge of it, on one of its outer arms, far from its gravitational center, a point astronomers call the Great Attractor. 500 million light-years, 100,000 galaxies. And this is just our supercluster, just our neighborhood within the cosmic web. But in 2023, researchers Aurélie Dupuis and Hélène Courtois published an analysis that delivered a quiet but significant blow to the standard cosmological model. When they examined the actual observed sizes of superclusters across the universe and compared them to what the standard model, lambda cold dark matter, predicted, they found that real superclusters are, on average, roughly 10 times larger than the model allows. Not slightly larger, not marginally outside predictions, 10 times larger. This is the same pattern Webb revealed at the scale of individual galaxies in the early universe. The universe, at every scale, Webb and modern surveys can probe, is more structured, more concentrated, and more organized than our best models predict. In the early universe, galaxies were too massive too soon. In the present universe, the structures those galaxies form are too large, too coherent, spanning distances that the standard model simulations simply do not produce. Something about the way structure forms, at every scale, across every era of cosmic history, is not captured by the equations we have built. Here is the thing most people have never fully absorbed. The 93 billion light-year bubble, everything we have described, every galaxy, every void, every supercluster, every anomaly Webb has found, all of it represents only what we can observe from our location in space, given the age of the universe. But the universe does not end at the edge of what we can see. Light from regions beyond our cosmic horizon simply has not had time to reach us yet. Those regions exist. We just cannot detect them. Our instruments are not limited by technology. They are limited by physics. The edge of our observable universe is not a wall. It is a veil, the point beyond which the universe's own history prevents us from seeing further. In 2011, a team of researchers from Oxford, Imperial College London, and Johns Hopkins University analysed data from the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. Using careful statistical analysis of the temperature fluctuations in that ancient light, they concluded that the total universe, the full, actual extent of all that exists, is at minimum 250 times larger than the observable portion. 250 observable universes, stacked edge to edge, would only just begin to span the real thing. 250 times everything we have ever described or detected. And that figure, 250, is a lower bound, a minimum estimate. It assumes the universe has a specific geometry that the data can constrain. But if the universe is spatially flat, meaning if parallel lines never converge, never diverge, and the geometry of space on the very largest scales is Euclidean, then no boundary exists at all. A spatially flat universe is infinite, truly, literally, mathematically infinite, extending without limit in every direction, containing not just 2 trillion galaxies, but an infinite number of them, containing, with certainty, every configuration of matter that physics allows, including, at sufficient distance, regions statistically indistinguishable from our own. Current measurements of the universe's geometry, from the Planck satellite's observations of the cosmic microwave background, marginally favour a flat or near-flat universe, not conclusively, not beyond all doubt. But the direction the data points is toward flatness, toward infinity. Let's step back and sit with what we have actually established here. You are on a planet orbiting an ordinary star. That star is one of roughly 200 to 400 billion stars inside the Milky Way. The Milky Way is one of more than 2 trillion galaxies inside the observable universe. The observable universe is, at minimum, 1/250th of the total universe, and the total universe may have no boundary at all. The scale does not flatten to abstraction when you hold it. Properly, it does the opposite. Each layer reveals that the previous one, the one that already seemed incomprehensible, was itself contained within something larger, and that larger thing within something larger still, and that somewhere far beyond everything we can detect, the same physical laws that govern the fall of rain and the rhythm of a heartbeat are operating, and have always been operating, across distances that have no name. This is not a cause for despair. The fact that we have mapped this much, that we have gone from knowing only our solar system to knowing the shape of our galaxy, to measuring the cosmic web, to detecting the edge of our observable bubble and inferring what lies beyond, in the span of a single century of scientific inquiry, represents one of the most extraordinary achievements in the history of any mind anywhere in the universe, as far as we know. But scale, by itself, is only part of what the universe is asking us to confront. because when researchers look at the expansion of all this scale, when they try to measure with precision how fast the universe is growing so they can understand its past and predict its future, something very strange happens. The number they measure depends on how they measure it, and the two most precise measurements humanity has ever made of that number do not agree. The Hubble constant, the number that describes how fast the universe is currently expanding, should be one of the most straightforward measurements in cosmology. You observe galaxies at known distances. You measure how fast they are receding. You divide. You have your answer. Humanity has now made that measurement two ways, with two different methods, using two of the most sophisticated observatories ever built. One method reaches back to the earliest light in the universe. The other measures the universe as it exists today, galaxy by galaxy, star by star. They get different answers, not slightly different, not within measurement uncertainty, different by a margin that physicists call 5 sigma, the threshold at which, in any other field of physics, a disagreement between two measurements is considered a confirmed discovery that something is wrong. And Webb, the telescope built partly to resolve this very disagreement, has now confirmed that neither measurement is in error. The universe is expanding, but the rate at which it is expanding appears to depend on when you ask the question, and no one yet understands why. Two measurements, both made with the finest instruments humanity has ever built, both conducted by teams of Nobel laureates and world-leading cosmologists, both verified, cross-checked and published in peer-reviewed journals, both representing decades of accumulated scientific effort. They disagree, not in a small way, not in a way that rounding errors or calibration drift can explain away. They disagree by a margin that, in the language of physics, crosses the threshold of a confirmed discovery, which means one of two things is true. Either one of our most precise instruments is wrong, in a way that has somehow escaped detection for years, or the universe itself behaves differently, depending on when in its history you measure it. And Webb, the telescope built, in part, specifically to resolve this disagreement, has now made it worse. Let's be precise about what we are measuring because the name can mislead. The Hubble constant, named after Edwin Hubble, the astronomer who first confirmed in 1929 that galaxies beyond our own exist and are moving away from us, describes the current rate at which the universe is expanding, not the Big Bang expansion, not the inflation that happened in the universe's first fractions of a second. The expansion happening right now, today, in the present universe, as every galaxy cluster recedes from every other galaxy cluster across the cosmic web. The way it works is this: the further away a galaxy is, the faster it appears to be moving away from us. Not because the galaxy itself is racing through space, but because the space between us and that galaxy is expanding, stretching like marks on a balloon being inflated, with each mark moving further from every other mark as the surface grows. The Hubble constant tells us exactly how fast that stretching is happening per unit of distance. Specifically, it describes how many kilometers per second a galaxy appears to recede for every megaparsec of distance between it and us. A megaparsec is a unit of cosmic distance equal to about 3.3 million light-years, roughly the distance between our Milky Way and the Andromeda Galaxy. So the Hubble constant answers a precise question. For every 3.3 million light-years of distance between us and a galaxy, how many additional kilometers per second is that galaxy moving away from us? That number governs everything. It determines the age of the universe. It determines its ultimate fate. It determines whether the cosmos expands forever or eventually reverses. Getting it right is not a technical nicety. It is one of the most consequential measurements in all of science. The first method for measuring the Hubble constant reaches back to the very beginning. The Planck satellite, launched by ESA in 2009, spent years mapping the cosmic microwave background with extraordinary precision. The cosmic microwave background is the faint afterglow of the Big Bang itself, ancient light, now cooled to just a few degrees above absolute zero, filling the entire sky in every direction. It was emitted when the universe was only about 380,000 years old, and it carries imprinted within its temperature patterns a precise record of the physical conditions at that moment. By analysing those patterns with extraordinary mathematical care, cosmologists can calculate, working forward through 13.8 billion years of known physics, what the expansion rate of the universe should be today. This is called the early universe method, and the Planck satellite's answer, published with exquisite precision, is 67.4 kilometers per second per megaparsec. That number, 67.4, is the universe's expansion rate as predicted from its own infancy, carried forward through time by the best equations we have. The second method measures the universe directly, today, in the present. It uses a technique called the cosmic distance ladder. The logic is straightforward. To measure how fast something is moving away, you need to know how far away it is. And measuring cosmic distances precisely is one of the hardest problems in astronomy. The solution, built over decades, is to chain together a sequence of overlapping distance measurements, each method valid at a particular range, each calibrated against the next, like a series of rulers, each one slightly longer than the last, stretching from our solar system outward to the most distant galaxies. The critical rungs of this ladder include a class of stars called Cepheid variables. Cepheids are stars that pulse, brightening and dimming in a regular rhythm like a slow heartbeat, and the speed of that pulse is directly tied to the star's true luminosity. The longer the period between pulses, the intrinsically brighter the star. This relationship, discovered by Henrietta Swan Leavitt at Harvard in 1912, means that by measuring how long a Cepheid takes to complete one pulse, you can calculate how bright it truly is. Then, by comparing that true brightness to how bright it appears to us, you can calculate precisely how far away it is. Beyond Cepheids, the ladder extends further, using Type 1a supernovae, a class of stellar explosions so consistent in its peak brightness that it functions as a standard beacon across billions of light years, allowing distance measurements to galaxies far beyond what Cepheids can reach. Adam Rees at Johns Hopkins University, a Nobel laureate in physics, one of the scientists who discovered that the universe's expansion is accelerating, led the team conducting the most rigorous local universe measurement ever attempted. His SH0ES team's answer, approximately 73 kilometers per second per megaparsec, 67.4 versus 73. The gap is roughly 8 to 9%. In everyday terms, 8% sounds modest, but in precision cosmology, where measurements are calibrated to fractions of a percent, an 8 to 9% disagreement between two flagship results is not a minor discrepancy. Expressed statistically, the gap sits at approximately 5 sigma, 5 standard deviations from agreement. 5 sigma is the threshold at which physicists declare a confirmed discovery. An 8% disagreement between two measurements at 5 sigma confidence is not noise, not drift, not a rounding error. 5 sigma means that if both measurements are correct, and the gap was simply the result of random chance, you would expect to see that outcome only once in roughly 3.5 million attempts. Physicists use 5 sigma specifically because it is the level at which the possibility that a result is accidental becomes negligibly small. The two best measurements of the universe's expansion rate are separated by a confirmed discovery-level disagreement, and it gets more complicated still. The most natural explanation, the first assumption most physicists reached for, was instrument error. Hubble Space Telescope had been operating since 1990. Its optics, its calibration, its aging detectors, perhaps something in the pipeline of the local measurement was subtly miscalibrated. Perhaps the Cepheid distances, or the supernova brightness standards, carried a systematic error that had compounded quietly through years of data. Perhaps the ladder had a bent rung. Webb was built, in part, specifically to test this. Webb's infrared vision, operating at wavelengths Hubble physically cannot access, was designed to re-examine the very Cepheid stars at the heart of the local distance ladder, free from the dust contamination and optical limitations that had always been potential sources of error in Hubble's measurements. Between 2023 and 2024, Rees's SH0ES team used Webb to re-observe the Cepheid variables that anchored their distance measurements. Webb confirmed Hubble's numbers. Precisely. Completely. Every concern about aging optics, about dust, about infrared bleed-through affecting Hubble's Cepheid photometry, Webb eliminated them. The Cepheid distances that SH0ES had measured with Hubble were correct. The local expansion rate, 73 kilometers per second per megaparsec, was not a measurement artifact. Adam Rees responded to the Webb confirmation with a statement that deserves to be quoted carefully. He said, "With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe." A Nobel laureate using the word misunderstood about the universe after eliminating every known source of instrumental error. That sentence is not hyperbole. That is a precise, measured statement from a physicist who has spent his career making precise, measured statements. And what it means is this: the Hubble tension is not going away. Two flagship space telescopes, Hubble and Webb, now both confirm the local measurement. The Planck satellite independently confirms the early universe measurement, and the gap between them at 5 sigma confidence is real. But here is where the story resists the clean resolution it seems to be approaching. Wendy Friedman, an astronomer at the University of Chicago and one of the most respected distance measurement scientists in the world, leads an independent team called CCHP, the Carnegie Chicago Hubble Program. Her team uses different standard candles, alternative classes of stars and stellar populations that offer independent routes up the cosmic distance ladder, ones that are less susceptible to the potential biases that might affect Cepheid measurements. Her team's published results place the local Hubble constant somewhere between 68 and 72 kilometers per second per megaparsec. That range straddles the divide. It does not align firmly with either Planck's 67.4 or Rees's 73, and her team has raised specific technical concerns, published in peer-reviewed journals, about the way Cepheid distances have been calibrated, suggesting that some of the tension may still have an observational origin, even after Webb's confirmation. This is not a fringe objection. Friedman's team has published independent results using Webb-based observations of their own and reached modestly different conclusions than Rees. The field currently has 3 well-credentialed, rigorously conducted measurement programs pointing toward 3 distinct, if partially overlapping, answers. The honest picture of the Hubble tension as of late 2025 is this: the 5 sigma gap between the earliest and most local measurements appears real and not attributable to simple instrument error. But within the local measurement community, serious scientific disagreement persists about the precise value. The early universe and late universe measurements disagree, and even among late universe measurements, full consensus has not been reached. What this means for the underlying physics is genuinely open. Some theorists have proposed that the standard cosmological model is missing a component of dark energy that was stronger in the early universe than it is today, something that would have accelerated early expansion slightly faster than current models account for, shifting the Planck prediction closer to local measurements. Others propose a 5th fundamental force operating at early times. Others suggest modifications to our understanding of dark matter's behavior. None of these proposals has been confirmed. Several contradict other well-tested aspects of cosmology. The tension has generated dozens of proposed solutions, and not one of them has survived contact with the full breadth of cosmological data without introducing new problems. The universe's expansion rate depends on when you measure it, or our model of the universe is incomplete, or both. As of December 2025, the Hubble tension remains the single most significant unresolved crisis in modern cosmology. Not a puzzle at the edges of understanding, a fracture at the center of it. Let's take a careful breath here and acknowledge what this actually means, because it is significant without being catastrophic, and extraordinary without being the end of science. The Hubble tension does not mean we know nothing. The two values, 67.4 and 73, differ by less than 9%. In absolute terms, cosmologists have measured the expansion rate of a 13.8 billion-year-old universe to within single-digit percentage agreement using two entirely different physical phenomena: quantum imprints in ancient light and the rhythmic pulsing of distant stars. That is a triumph of human measurement, even in its disagreement. What the tension reveals is that the standard cosmological model, lambda cold dark matter, may be missing something real, something that affects how the universe expanded in its early stages differently from how it expands today. Something that either our early universe physics or our late universe physics, or both, has not yet fully captured. Think of it this way. Imagine you are trying to calculate the age of a tree by counting its rings from the outside, and you also have a dated photograph of the tree as a sapling. If your ring count and your photograph give you different ages for the same tree, one of three things is true. Your ring counting method has an error. Your photograph has been misdated, or the tree grew at a different rate during different periods of its life than you assumed. Two of those three possibilities point to something real and interesting about the tree. Two of the three possibilities for the Hubble tension point to something real and interesting about the universe. The most intellectually honest position, the one most cosmologists actually hold, is that the tension is a genuine signal, a signal pointing toward physics we have not yet discovered. New particles, new fields, new behavior from dark energy, something that operated differently in the early universe than it does today, and that left its fingerprint in the gap between these two numbers. We do not yet know what that something is. A 9% disagreement in the Hubble constant. Galaxies 10 times more common in the early universe than the model predicted. Black holes 400 times more disproportionate than they should be. Oxygen in a galaxy that had no time to make it. Every one of these crises points inward, toward the question of whether the standard model of cosmology, the framework that has governed our understanding of the universe for 40 years, is complete. Whether the equations we have built describe the full reality of what the cosmos is made of and how it behaves. Dark energy, the name physicists gave to whatever is causing the universe's expansion to accelerate, the mysterious component that makes up roughly 68% of everything in existence, has always sat inside the standard model as a fixed constant, a permanent feature of space itself, unchanging, stable, a number baked into the fabric of reality from the moment of the Big Bang. But in the last 2 years, the largest galaxy survey ever conducted, mapping not thousands of galaxies, not millions, but tens of millions, has produced evidence that dark energy is not constant at all, that it has changed over time, that the force reshaping the entire cosmos, the force that will ultimately determine whether the universe expands forever, tears itself apart, or one day collapses inward, is not the stable, predictable thing the standard model assumed, and the data pointing toward that conclusion has just grown stronger. The Hubble tension told us our two best measurements of the universe's expansion rate disagree, but that disagreement, as unsettling as it is, at least concerns a number, a rate, a value, a measurement that might one day be reconciled when the right piece of physics is found. What the next crisis concerns is not a number. It concerns the nature of the force reshaping everything. 68% of the entire energy content of the universe, more than 2/3 of everything that exists, is made of something we cannot see, cannot touch, cannot detect with any instrument, and cannot explain from first principles. We gave it a name, dark energy, but naming something is not the same as understanding it. And for decades, the one comfort cosmologists held onto was this: whatever dark energy is, it appears to be constant, stable, woven into the fabric of space itself as a permanent, unchanging feature, like a tension in the very geometry of the cosmos. That comfort may no longer be available. To understand what has changed, you need to understand what dark energy is supposed to be, and why physicists settled on the simplest possible description of it in the first place. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, made a discovery that earned them the Nobel Prize in Physics in 2011. Studying Type 1a supernovae at extreme distances, they found that the universe's expansion was not slowing down, as gravity would demand. The universe was accelerating. Something was pushing space outward with increasing force, overpowering the gravitational pull of all the matter in the cosmos. Whatever was causing that acceleration became dark energy. Ordinary matter, every atom in every star, every planet, every human body, every molecule of gas drifting through the void, makes up approximately 5% of the total energy content of the universe. 5%. Think of everything you have ever seen or touched. Every mountain and ocean, every galaxy and every photograph Webb has ever taken. All of it. 5% of what is out there. Dark matter, the invisible gravitational scaffolding that holds galaxies together, which we can detect only through its gravitational effects, adds another roughly 27%. And dark energy fills the remaining 68%. The universe is mostly made of things we do not understand. And dark energy, the dominant component, the majority shareholder, is the least understood of all. The simplest mathematical description of dark energy treats it as what physicists call a cosmological constant. Einstein first introduced this concept in 1917, originally as a way of preventing his equations from predicting an expanding universe, before Hubble's observations proved expansion was real, and Einstein called it his greatest blunder. But after 1998, the cosmological constant was revived, not as a correction to prevent expansion, but as the mathematical representation of a universe whose expansion is accelerating. In this model, dark energy is not a substance, not a field, not something that changes or evolves. It is a fixed property of empty space itself, every cubic centimetre of vacuum possessing an identical, permanent, unchanging energy density. As the universe expands and new space is created, that new space brings with it the same constant dark energy. Expansion feeds expansion. Acceleration grows. The cosmological constant had one powerful virtue: it matched the data. For 20 years, every observation pointed to a universe consistent with a fixed, stable, dark energy. It was not a satisfying explanation. Physicists deeply want to know what dark energy actually is, but a constant that fit the data was, for a time, good enough. And then the data changed. The Dark Energy Spectroscopic Instrument, known as DESI, sits atop Kitt Peak National Observatory in Arizona, at an elevation of roughly 2,000 meters, or about 6,500 feet above the Sonoran Desert. DESI is not a single telescope in the conventional sense. Its power comes from 5,000 precisely positioned optical fibers, each one capable of capturing the light of a single galaxy simultaneously, feeding it into spectrographs that split that light into its constituent wavelengths and extract, with extraordinary precision, the galaxy's distance and recession speed. In April 2024, the DESI collaboration released their first-year results. They had mapped 6 million galaxies, 6 million individual data points spread across cosmic history, each one a measurement of where the universe was and how fast it was expanding at a different moment in time. Together, these 6 million galaxies form a kind of three-dimensional history of cosmic expansion, stretching back billions of years. What the data showed was a hint, statistically expressed at 3.9 sigma, that dark energy had not been constant across cosmic history, that its strength, its influence on the rate of expansion, appeared to have varied over time. 3.9 sigma is significant, In particle physics, 3 sigma is enough to claim evidence of a new phenomenon. 4 sigma warrants serious attention. 5 sigma is the discovery threshold. 3.9 sigma from a single survey of 6 million galaxies was enough to make the entire cosmological community lean forward. Then, in March 2025, DESI released their second data release, 18.7 million galaxies, the largest galaxy survey in human history at that time, and the evidence for evolving dark energy strengthened to 4.2 sigma. That represents a confidence level of 99.995%, meaning the probability that this signal is a random statistical fluctuation, that dark energy is actually constant, and this is all noise, is roughly 1 in 20,000. 1 in 20,000. That is not noise. That is a signal. But the specific character of what DESI found is what makes this truly disturbing. The data suggests that in the early universe, billions of years ago, dark energy may have been in what physicists call a phantom phase. This requires careful explanation, because the word phantom here has a precise and deeply strange technical meaning. In standard cosmology, the equation of state parameter of dark energy, a number physicists label W, which describes the relationship between its pressure and its energy density, is exactly -1 for a cosmological constant. -1. That is the value that produces steady, constant acceleration of the universe's expansion. For dark energy to be in a phantom phase means its W value drops below -1, below the floor of the cosmological constant, and below that floor, the physics changes character entirely. Phantom dark energy does not just accelerate expansion steadily, it accelerates it at an increasing rate, growing more powerful over time rather than holding constant, producing a universe that does not merely expand forever, but expands ever faster, without limit, until the expansion rate itself becomes infinite. The DESI data suggests dark energy may have been in this phantom regime in the past, and has since weakened, pulling back toward or through the cosmological constant value. Here is why this is so deeply problematic for the standard model. The cosmological constant, W equals -1, is not just a number. In the standard model's mathematics, it is a divide, a wall. Dark energy cannot cross from above it to below it and back again. The equations do not provide a mechanism for that crossing. No known field in physics crosses the phantom divide without producing instabilities or infinities that break the mathematics entirely. Yet the DESI data suggests the universe crossed it anyway. The standard model has no mechanism for what the universe appears to have done. It contains no equation, no field, no particle, no force that accounts for dark energy beginning below the divide, strengthening and then weakening back across it. If this signal holds and strengthens with additional data, it does not simply require a new parameter in the existing model. It requires new physics. Fundamentally, new physics. Physics that does not yet exist in any confirmed theory. And this is where the story arrives at its most personal question. Because dark energy does not just describe an abstract cosmological parameter, dark energy determines how the universe ends. Not metaphorically, literally. The ultimate fate of the cosmos, every galaxy, every star, every atom, depends on what dark energy does next. And right now, 3 distinct endings remain physically possible, 3 different futures for everything that exists, and not one of them has been ruled out. The first ending is called the Big Freeze. In this scenario, dark energy holds at approximately its current strength, stable, constant, or slowly weakening to a permanent floor. The universe expands forever, but at a manageable, steady rate. Gravity continues to hold galaxies and solar systems together for an extraordinarily long time. Stars continue to burn. New stars continue to form from gas clouds for roughly 100 trillion years. That is 100,000 billion years, a timescale so vast that the current age of the universe represents less than 1/10,000th of it. But eventually, the last star exhausts its fuel. The last red dwarf flickers out. Black holes evaporate over timescales almost beyond language, and the universe drifts, cold and dark and silent, toward maximum entropy, a state of perfect, featureless equilibrium where no gradient of energy remains to drive any process, any reaction, any event. Heat, death, perfect stillness, not destruction, but the final completion of disorder. The second ending is the Big Rip. If dark energy returns to phantom behavior, if its strength begins growing again rather than holding steady or weakening, the consequences become extreme. Phantom dark energy does not merely keep galaxies apart. It eventually overwhelms every other force in the universe, systematically tearing apart every gravitationally or electromagnetically bound structure, working inward from the largest scales to the smallest. Galaxy clusters, which gravity holds together across millions of light years, would be torn apart roughly 2 billion years before the final moment. Individual galaxies would dissolve shortly after. Solar systems would be unbound. Planets would drift from their stars. And in the final minutes, the last 30 minutes before the end of everything, the Earth itself would be pulled apart, its material dispersed into the expanding void. In the final seconds, molecules would be ripped into atoms, atoms into subatomic particles, and in the last fractions of a second, space itself would tear apart at every scale simultaneously, in a catastrophe with no analogy in anything we have ever observed or imagined. The third ending arrived in 2025 from an unexpected direction. Young-wook Lee at Yonsei University in South Korea published an independent analysis of Type 1a supernova data, suggesting something that cuts directly against the Standard Model's long-held assumption of perpetual acceleration. The universe may already be decelerating, slowing down. If Lee's analysis holds up under further scrutiny, and it remains contested, not confirmed, dark energy may be weakening faster than even DESI's data suggests, weakening enough that gravity, patient and pervasive, eventually wins. The expansion stalls, reversal begins, and over an almost incomprehensible timescale, everything that the Big Bang spread outward over 13.8 billion years begins to fall inward again. Galaxies merging, temperatures rising, structures collapsing, until all the matter and energy in the observable universe is compressed back into a singularity, the Big Crunch. Not an expansion that ends in silence, but a contraction that ends in fire. 3 endings, 3 completely different physical destinies, each one governed by a different behavior of the same force, each one consistent with some portion of the current data, and none of them yet eliminated. Let's be precise about where the evidence actually stands, because precision matters here more than almost anywhere else in this story. DESI's 4.2 sigma result is not a confirmation that dark energy is evolving. It is a very strong indication, the strongest yet, that the simplest model, the cosmological constant, may be insufficient. 4.2 sigma means the data is unlikely to be noise. It does not mean the specific interpretation, phantom dark energy crossing the divide, is confirmed. The DESI team is careful to say that multiple theoretical models could potentially produce similar signatures in the galaxy distribution data, and that distinguishing between them will require more data, more precise measurements, and independent confirmation from other surveys. What it does mean, unambiguously, is that the cosmological constant, the simplest, cleanest, most mathematically elegant description of dark energy, is under genuine pressure, serious pressure, from the most comprehensive galaxy survey ever conducted, and the DESI results do not stand alone. The Hubble tension, that persistent disagreement in expansion rate measurements, may itself be connected to evolving dark energy. Some of the theoretical models proposed to resolve the tension involved dark energy that behaved differently in the early universe than it does today. The same physics that could explain the Hubble tension might also explain DESI's signal, or it might not. That connection remains an open and active area of research. What we are left with is this: the force that constitutes 68% of the universe, the dominant component of everything that exists, has been described for 25 years by the simplest possible assumption that it is constant, fixed, and permanent. That assumption served us well, and now the data is quietly, persistently, insistently suggesting it may not be true. The universe has a behavior we assign to it, and it may be in the process of correcting us. Dark energy changing over time, structures forming too early and too large, black holes too massive too soon, two measurements of expansion that cannot be reconciled, galaxies 10 times more common than predicted, oxygen in a cosmos too young to have made it. Every one of these anomalies lives at a different scale, in a different era, measured by a different instrument, and yet they point collectively in the same direction, toward a universe that is more structured, more active, more organized, and more deeply at odds with our models than 40 years of careful cosmology predicted. But every problem we have examined so far has had one thing in common. Each one asks whether our model of the universe's contents and history is correct, whether the equations governing gravity, expansion, and matter are complete. None of them has yet asked the most foundational question of all, the question beneath all the equations, the assumption so basic it is rarely stated aloud, the premise on which the entire edifice of modern cosmology rests. The cosmological principle, the idea that the universe at the largest scales is smooth and uniform in every direction, has been the bedrock of every model we have built, every prediction we have tested, every tension we have measured. Without it, the standard model cannot function. Without it, the Planck results, the DESI survey, the distance ladder, none of them can be interpreted the way we currently interpret them. And Webb's deep survey data, combined with the largest structure ever mapped in the observable universe, has now placed that foundational assumption under direct observational challenge. Not a tension, not a hint. A structure 10% of the width of the entire observable universe, 8 times larger than any structure the cosmological principle permits. And it exists. A structure 10% of the width of the entire observable universe, 8 times larger than any structure the laws of physics say can exist. Confirmed, measured, real. Before we arrive there, we need to understand what it threatens, because this is not simply another anomaly in a growing list of anomalies. This goes deeper than galaxy formation models or black hole growth rates or dark energy behavior. Those are all questions about the contents of the universe, about what the universe contains and how those contents behave. What the Hercules Corona Borealis Great Wall threatens is something beneath all of that, the foundation itself, the assumption so basic, so baked into every equation and every prediction and every measurement we have examined in this entire journey, that most cosmologists rarely state it explicitly at all. It is called the cosmological principle, and without it, modern cosmology as we know it cannot function. Let's be precise about what the cosmological principle claims, because precision matters enormously here. The cosmological principle states that the universe, when viewed at sufficiently large scales, is homogeneous and isotropic. Those two words carry the entire weight of the assumption. Homogeneous means the universe looks the same everywhere. No region of space is fundamentally different from any other. Isotropic means the universe looks the same in every direction. No direction in space is fundamentally different from any other. Together, these two properties describe a universe that has no preferred location and no preferred direction. A universe that is, at the largest scales, smooth, uniform, without special features. This is not a minor assumption. This is the assumption on which every major equation in modern cosmology is built. The Planck satellite's mapping of the cosmic microwave background assumes it. The DESI galaxy survey assumes it. The distance ladder assumes it. The standard cosmological model, lambda cold dark matter, is derived from Einstein's equations of general relativity specifically under the condition that the cosmological principle holds. Remove it, and the entire mathematical framework needs to be rebuilt from the ground up. The principle has deep observational support at the scales it was originally designed to describe. Look at the cosmic microwave background, the ancient light filling the sky from every direction, and the temperature variations across it are incredibly small. 1 part in 100,000. A smoothness that, on the scales of the early universe, was remarkable confirmation of homogeneity. At scales of hundreds of millions of light years, galaxy surveys show a universe that does average out. The cosmic web, its filaments and voids and clusters, appears roughly similar from one region of the cosmos to another when you zoom out far enough. The critical boundary, the scale at which structure is supposed to fully smooth out into uniformity, sits at approximately 1.2 billion light-years. Below that scale, structure is expected and observed. Galaxies cluster, filaments form, voids open. All of that is consistent with the cosmological principle. But above 1.2 billion light-years, the standard model makes a specific prediction. No coherent structure should persist. The universe should average into featureless uniformity. The largest building blocks of the cosmic web should blur together. No single gravitationally or statistically coherent object, no structure that behaves as a single entity, should span more than roughly 1.2 billion light-years. That is the prediction. That is the line in the sand. And now we need to talk about what is sitting on the wrong side of it. In 2013, a team of Hungarian and American astronomers, István Horváth, Jon Hakila, and Zsolt Bageli, published a study that attracted serious attention in the cosmological community. They were not studying galaxies, they were studying gamma-ray bursts, the most violent explosions in the observable universe, occurring when massive stars collapse or when neutron stars merge. These bursts are so luminous that they can be detected across billions of light-years of space, making them extraordinary tracers of where matter, and therefore structure, exists in the distant universe. What Horváth's team found when they mapped the positions of a large catalogue of gamma-ray bursts was a clustering, a region, of the sky in the direction of the constellations Hercules and Corona Borealis, where gamma-ray bursts appeared statistically far more often than random distribution would predict. A concentration that, when mapped across its full extent, outlined a coherent structure spanning approximately 10 billion light-years in its longest dimension. 10 billion light-years. To understand what that number means, consider this. The entire observable universe, the full 93 billion light-year bubble containing every galaxy Webb has ever photographed, spans 93 billion light-years from one edge to the other. 10 billion light-years is roughly 11% of that full diameter. The Hercules Corona Borealis Great Wall, if real, would span roughly 1/9 of the observable universe's entire width. And the cosmological principle permits no coherent structure larger than about 1.2 billion light-years. 10 billion is more than 8 times that maximum. This is not a structure that sits slightly outside the model's predictions. This is a structure that, if confirmed, violates the cosmological principle so dramatically that the violation cannot be explained by any adjustment to the standard model's parameters. You cannot tune a constant, revise an initial condition, or add a new particle and produce a structure of this scale. The cosmological principle would simply have to be wrong. But in 2013, the statistical significance of the Hercules Corona Borealis Great Wall was real but not overwhelming, suggestive but not yet at the level where the community felt compelled to treat it as confirmed. Some researchers pointed to potential selection biases in the gamma-ray burst catalogue. Others noted that the sample sizes were not yet large enough to fully exclude the possibility that the clustering was a statistical artifact. The structure was contested, and then in April 2025, an expanded analysis was published. Using a substantially larger and more carefully curated dataset of gamma-ray bursts, correcting for observational biases the earlier study could not fully address. The April 2025 analysis confirmed the Hercules Corona Borealis Great Wall at increased statistical significance. The structure did not shrink under scrutiny. It did not dissolve into noise as the sample grew. The clustering held, strengthened. The probability that the observed concentration of gamma-ray bursts in that region of the sky is a random statistical fluctuation that no real structure exists became, under the expanded analysis, vanishingly small. This is the pattern that appears again and again in Webb-era cosmology. An anomaly is flagged. The community responds with legitimate caution. Better data is gathered, and the anomaly gets stronger, not weaker. The galaxy formation problems did not resolve as Webb accumulated more observations. They deepened. The black hole mass ratio problem did not shrink. 341 little red dots appeared. The Hubble tension did not disappear when Webb re-examined the Cepheids. It was confirmed. And the Hercules Corona Borealis Great Wall did not dissolve when more gamma-ray bursts were mapped. It held. Every exit from these anomalies that seemed available in the early data has closed, and Webb's own deep field data adds a separate, independent layer of pressure. The large-scale structure that Webb detects in the early universe, the way galaxies cluster and connect across hundreds of millions of light-years at redshifts far higher than any ground-based survey can reach, consistently shows structure appearing earlier and more organized than lambda cold dark matter predicts. Not dramatically, not as extreme as the Hercules Corona Borealis Great Wall, but systematically, persistently, pointing in the same direction. The universe is more structured than the standard model allows, at every scale, at every epoch, in every data set. Here is the deepest contradiction that emerges from all of this. The cosmological principle is not simply one assumption among many. It is the load-bearing wall of the entire edifice. Every tension we have examined, the Hubble constant disagreement, the DESI dark energy signal, the galaxy formation crisis, was identified, measured, and expressed using tools that assume the cosmological principle is true. The Planck satellite's precision measurements of the cosmic microwave background are interpreted within a mathematical framework that requires homogeneity and isotropy. The DESI survey's 18.7 million galaxies are analyzed using statistical methods that assume large-scale uniformity. The distance ladder that produced the local Hubble constant assumes that the physics of Cepheid stars and Type 1a supernovae is the same everywhere in the universe, which is only guaranteed if the cosmological principle holds. If the cosmological principle is wrong, if the universe has genuine large-scale structure persisting far beyond the predicted smoothing scale, then every measurement we have discussed in this journey may carry a systematic uncertainty we have not accounted for. The Hubble tension might partly reflect real large-scale inhomogeneity in the universe's expansion rate. The DESI signal might be influenced by structure that the standard model did not predict, and the analysis did not correct for. Even the Planck results, extraordinary as they are, rest on an assumption that the universe we see from our location in the Milky Way is representative of the universe as a whole. An assumption that a 10 billion light-year structure, if real, directly contradicts. And here is what makes this the deepest paradox of all. The cosmological principle was not invented arbitrarily. It was adopted because it works, because a century of cosmological observation, from Hubble's first measurements of galactic recession to Planck's precision mapping of the ancient sky, produced a consistent, coherent, mathematically beautiful picture of a universe that behaves as if the cosmological principle is true. The Standard Model is not naive. It is the product of the most rigorous scientific enterprise humanity has ever undertaken. And yet, the universe keeps producing things the Standard Model says cannot exist. Let's be careful, as always, about where the confirmed science ends and the open questions begin. The Hercules Corona Borealis Great Wall is a real and statistically significant clustering in the gamma-ray burst distribution. That much is established. What remains actively debated, and honestly debated, by serious researchers using the same data, is whether this clustering truly represents a gravitationally coherent structure in the classical sense, or whether it reflects something more subtle, a large-scale fluctuation in the density of matter that does not require revising the cosmological principle, but does require refining our understanding of how structures this large can be traced by gamma-ray burst distributions. The distinction matters. A gravitationally coherent structure, one that formed and is held together by the gravitational interaction of its constituent matter, would directly violate the cosmological principle at a fundamental level. A statistical density enhancement, a region where matter is slightly more abundant than average over a vast scale, but not bound or coherent in the physical sense, might be compatible with modified versions of the Standard Model, though it would still represent a significant challenge. The 2025 analysis leans toward genuine structure, but the debate in the literature is ongoing, and that is how science should work, carefully, rigorously, without premature conclusions. What is not in genuine scientific debate is the direction the data is pointing. Every major observational program of the last decade, Webb, DESI, Planck, and the gamma-ray burst surveys, has found a universe that is more structured, more asymmetric, and more surprising at large scales than the Standard Model predicted. Not in one data set, or two, or three. Systematically, persistently, across independent instruments operating on independent physical principles. The cosmological principle may be an approximation of reality rather than a precise description of it. And if that is true, it means the universe has large-scale features we have not yet mapped, not yet understood, and not yet incorporated into our equations. Features that could be reshaping every other measurement we have made, quietly, systematically, in ways we are only beginning to detect. Think about what that means for a moment. Cosmology has been extraordinarily successful precisely because it assumed the universe was, at the largest scales, simple. That simplicity, homogeneous, isotropic, smooth, was what made the equations tractable, what made predictions possible, what made the Standard Model work as well as it did, for as long as it did. The universe may be under no obligation to remain simple. Every crisis we have followed in this journey, the early galaxies, the impossible oxygen, the premature black holes, the Hubble tension, the evolving dark energy, and now the threatened cosmological principle, shares a common feature. Each one was discovered in a specific era of history. Our era, the era of Webb, the era of DESI and Planck, and combined telescopic power that no previous generation of scientists possessed. But here is something we have not yet considered: the ability to ask these questions, to see galaxies at the edge of the observable universe, to measure the ancient light of the Big Bang, to detect oxygen in a galaxy that has no right to contain it. This ability is not permanent. The universe is not a static archive patiently awaiting our instruments. The universe is moving, and it has been moving in one specific direction since the moment of the Big Bang. Every second, more of the universe moves beyond the cosmic event horizon, the boundary past, which expansion carries galaxies so fast that their light can never reach us no matter how long we wait. Every second, the window through which we can read cosmic history gets slightly smaller. The anomalies Webb found, the structures that should not exist, the elements that arrived too early, the black holes that grew too fast, all of them were visible because we live in a specific, narrow window of cosmic time where enough of the universe's history is simultaneously observable and interpretable, where the light from 13.8 billion years of events is still arriving, where the ancient and the present coexist in the same sky. That window is not permanent, and we may be much closer to the end of it than we have ever fully appreciated. The window is closing, not metaphorically, not as a figure of speech borrowed from urgency or drama, physically, irreversibly, as a direct consequence of the same expansion that has been pushing galaxies apart since the moment of the Big Bang. The universe is right now erasing its own history, carrying evidence beyond the reach of any instrument we could ever build, at a rate that no engineering, no technology, and no future civilization can reverse. We arrived in time to read some of it, but we need to understand what that means and what it will mean for everyone who comes after us, to feel the full weight of what Webb and every telescope before it has actually accomplished. Let's be precise about what the window closing actually means, because the mechanism is specific and the consequences are permanent. The universe is expanding. Every galaxy cluster is moving away from every other galaxy cluster. And because space itself is stretching, not because galaxies are racing through fixed space, but because the fabric of space between them is growing, galaxies at sufficient distances are receding from us faster than light can cross the gap. Not because they are breaking any law of physics, because space between us and them is expanding faster than light can traverse it. This creates what physicists call the cosmic event horizon. Think of it this way. Imagine you are standing on a moving walkway in an airport, walking toward an exit. If the walkway is carrying you backward faster than you can walk forward, you will never reach the exit, no matter how long you walk. The cosmic event horizon works on the same principle, but for light. Galaxies beyond a certain distance are being carried away from us by the expansion of space faster than light from those galaxies can travel toward us. Their light is, right now, on a journey it will never complete. It will travel toward us for billions of years, and the gap between it and us will grow faster than it can close. Those galaxies are, in a physical and permanent sense, already gone from our future. We can still see them now, because the light they emitted billions of years ago is still arriving, but the light they are emitting today will never reach us, and no amount of waiting, no improvement in telescopes, no future civilization of any sophistication can change that. The horizon is not a technological problem. It is baked into the geometry of an accelerating universe. Right now, within the observable universe, roughly 2 trillion galaxies exist within our cosmic horizon, the boundary of what we can, in principle, detect. Not all of them are visible today with current instruments, but in principle, given sufficient time and sufficiently powerful telescopes, they are reachable by light. That number is shrinking. Every second that passes, the expansion of space carries more galaxies across the event horizon and out of any possible future contact. Not out of our current observable universe. That boundary is defined by what light has had time to reach us since the Big Bang, and it stays roughly fixed from our perspective as the universe ages. But out of our reachable universe, the set of galaxies whose light can still, even in principle, ever reach us again. Based on current measurements of the universe's expansion, astronomers estimate that within approximately 100 billion years, a timescale about 7 times longer than the universe's current age, every galaxy beyond our local group will have crossed the horizon permanently. Every single one. The Virgo cluster, the vast filaments of the cosmic web, the superclusters whose true sizes only now exceed our model's predictions, the distant galaxies Webb has photographed at the edge of observability, all of them will be gone, not destroyed, but carried beyond any possible communication, beyond any possible observation, beyond any possible knowledge. What will remain visible to any civilization alive at that point will be the local group, the roughly 50 to 60 galaxies gravitationally bound to the Milky Way, held together by their own gravity against the expansion of space, a small cluster of stellar systems drifting in what will appear, from the inside, to be an empty, featureless, infinite dark. And here is what makes this more than a remote astronomical fact. Picture a civilization arising in that future universe, 100 billion years from now. Not primitive. Assume they are as scientifically sophisticated as we are, or more so. They have built telescopes. They have mastered mathematics and physics and spectroscopy. They have looked at the sky with every instrument their ingenuity can produce. What will they find? No cosmic microwave background radiation. The CMB, the ancient light of the Big Bang that fills our entire sky and provided humanity with its most precise measurement of the early universe, will by then have been stretched by the continued expansion of space to wavelengths so long and so cold that no instrument can practically detect it. The relic glow of creation, which Planck mapped with extraordinary precision, and which gave us the Hubble constant and the geometry of the universe, and the first glimpse of the cosmic web seeds, gone, diluted into undetectable silence. No galactic recession data. Edwin Hubble's foundational discovery that distant galaxies are moving away from us at speeds proportional to their distance, the discovery that revealed an expanding universe and ultimately led to the Big Bang model, will be unrepeatable, because the galaxies that provided that data will no longer be visible. No recession, no redshift, no expansion signal. The universe will appear, by every measurement that civilization can make, to be perfectly static. No evidence of the Big Bang at all. That future civilization, applying the same rigorous logic and honest methodology that produced the finest cosmology in our era, will reach a conclusion that is scientifically impeccable given their available evidence. The universe is a single stellar system, perhaps surrounded by a handful of neighboring systems, drifting in infinite static space. No origin event, no expansion, no cosmic history, no web of 2 trillion galaxies, no 14 billion year narrative of structure formation and stellar generation and chemical enrichment. They will be wrong. Not because they are less intelligent or less careful than we are, because the evidence will be gone. The entire history of cosmology, the Big Bang, the expanding universe, the CMB, the galaxy clusters, the structure Webb has revealed in such unsettling detail, will be, to that future civilization, permanently and irreversibly unknowable, not forgotten, never known. This is the deepest truth the universe has quietly been building toward throughout this entire journey. We live in the only era in which the full depth of cosmic history is simultaneously observable and legible. The light from the earliest galaxies, 300 million years after the Big Bang, barely formed, already more massive than our models allowed, is arriving at Webb's mirrors right now. The cosmic microwave background, the afterglow of the Big Bang itself, is filling the sky right now. The recession of 2 trillion galaxies, the very evidence of the universe's origin and expansion, is measurable right now. Every piece of evidence that makes modern cosmology possible is present in the sky, simultaneously at this specific moment in cosmic history. This will not always be true. It has not always been true in the past. In the universe's very first hundreds of millions of years, no planet existed from which the cosmos could be observed at all, and it will not be true in the distant future, when the evidence will have been scattered beyond recovery. We occupy a narrow window, not a geological window, not a historical window, a cosmic window, an era defined by the simultaneous presence of 13.8 billion years of accumulated evidence, all still within reach, all still legible, all still answerable. Webb has been operational for approximately 3.5 years. In that time, not decades, not a generation, 3.5 years, it broke the galaxy formation model that governed cosmology for 40 years. It confirmed the Hubble tension that 2 generations of physicists hoped would resolve itself. It detected oxygen in a galaxy at an age when the universe had barely learned to make stars. It catalogued hundreds of black holes whose existence no accepted theory can explain. The list of what it has broken is already longer than the list of what it confirmed, and it has decades of operational life remaining. Step back from the anomalies for a moment. Hold all of them at once. The early galaxies, the impossible chemistry, the premature black holes, the Hubble tension, the evolving dark energy, the threatened cosmological principle, the structure 8 times larger than any structure should be. What is the pattern? The universe built its largest, most extreme, and most violent structures first. In the first few 100 million years, a cosmic infancy by any measure, it was already assembling galaxies of shocking mass, black holes of staggering disproportionality, chemical complexity that required multiple stellar generations to produce. The early universe was not a quiet nursery. It was, by the evidence Webb has accumulated, the most active and extreme era in cosmic history. Hotter, denser, more productive per unit of time, more chaotic, more structurally ambitious than anything that has come since. What surrounds us now, the relatively calm, slowly evolving universe of today, where stars form at a fraction of their ancient rate, where galaxies have settled into stately spirals and ellipticals, where the cosmic web drifts in slow expansion, this is the quiet aftermath, the long, cooling exhale after a violent birth. The universe's dominant mode was always chaos. What we experience as the normal cosmos is a temporary late-stage calm that will not persist indefinitely, and we arrived just in time to read it, just in time to see the ancient light still in the sky, just in time to build the instruments sensitive enough to pull chemistry from galaxies 280 million years old, just in time to map the structure of a cosmic web that future civilizations will never know existed. The universe is not terrifying because of its size. We have known it was large for a century. The size is almost comfortable now, familiar in its incomprehensibility, a number we have learned to hold without flinching. The universe is terrifying because the more precisely we look, the less we recognize. Every improvement in our instruments, every leap from Hubble to Webb, from ground-based surveys to DESI's 18.7 million galaxies, from single-dish radio to the combined power of ALMA and Webb working in concert, has revealed not greater confirmation of what we predicted, but greater departure from it. The standard model does not become more accurate as we see more. It becomes less adequate, more strained, more in need of revision at its foundations. This is not a cause for despair. This is the sign of a science that is genuinely working, genuinely engaging with a universe that has not agreed to be simple on our behalf. On Christmas morning, 2021, we launched the most complex machine ever sent to space. And in July 2022, Webb released its first deep field image. Thousands of galaxies, each one a system comparable to our Milky Way, packed into a patch of sky the size of a grain of sand held at arm's length. That image has not shrunk in significance since then. It has grown, because now we know what was hiding inside it. Galaxies that should not yet exist. Chemistry that required a timeline the universe had not yet provided. Black holes that the equations of physics cannot account for. The ancestors of structures so large, they challenge the foundational assumption beneath every cosmological model we have ever built. Behind that grain of sand, behind that single, specific, vanishingly small patch of sky, was not just the early universe. It was the earliest evidence of everything we do not yet understand about the universe. The first glimpse of a cosmos operating by rules we have not fully found, at scales we cannot fully observe, toward an ending we cannot yet determine. That grain of sand held at arm's length, and inside it, a history more complex, more extreme, and more surprising than 40 years of careful science anticipated. You have travelled a considerable distance tonight, from a Christmas morning launch to the edge of the observable universe and back, through black holes that should not exist and oxygen in skies too young to contain it. Sit with that for a moment. Not the anxiety of unanswered questions, but the rare and genuine feeling of having looked at something real, and having looked at it honestly, without flinching from its strangeness. That is what science actually feels like from the inside. Not certainty, but the sustained willingness to keep looking, even when looking reveals more mystery than it resolves. We are not at the end of understanding. After everything, after all of this, we are still, remarkably, at the very beginning. The universe continues, patient, indifferent, extraordinary, unfinished, operating by rules we have not fully found, at scales we cannot fully observe, toward an ending we cannot yet determine. And somewhere right now, Webb is still looking, still accumulating photons that left their source before our sun existed, still finding things that were not supposed to be there, still building, image by image and spectrum by spectrum, the most honest portrait of reality that our civilization has ever attempted. The window is not closing tomorrow, but it is closing, and we arrived just in time. Every telescope we have ever built was built for the same reason, not to find answers, to earn better questions, and tonight Webb gave us the best ones we have ever had. A galaxy with oxygen it had no time to make, black holes that should not exist, a universe expanding at a rate that depends on when you ask, structures so large they challenge the very foundation of everything we thought we knew, not failures of science, invitations, the universe quietly setting the next question on the table and waiting to see if we are brave enough to sit down with it. You watched all of this tonight. You stayed. You followed every impossibility to its edge and looked over. That is not a small thing. We are not at the end of understanding. We are, after everything Webb has shown us, after every broken model and every shattered prediction, still, remarkably, at the very beginning. And that beginning belongs to everyone curious enough to look. If tonight made you feel something, if it made the sky outside feel different, leave a like, subscribe, and stay close. Because the universe is not finished surprising us, and neither are we.